Okay, I will start this practical session. I'm Tae-Yeon Hwan, and due to time issue, I would like to proceed this practical session until the practical session ends, even after 12 o'clock. So those who have any plans after 12 o'clock, you have to leave, but we are going to continue the class. This class will be uploaded to the classroom. So, and if you have any question about transformer code, feel free to mail me. This is my mail, or feel free to ask classroom. So in this practical session, we will learn transformer and the table. This is a table of contents. We will prepare the input of data set and implement transformer from very basic building blocks and train and evaluate the transformer and visualize the tension. First, please download your download package which needs for these practical sessions. In this practical session, I will do not explain prepare input or train and evaluate, because I think you guys already learned how to prepare data set and train and eval the model. So I think this is, I think, the same as that you learned in week 9. So in this practical session, I will focus on how to implement the transformers. So first, and then we have to prepare the input data set. So download that data set from this GitHub and unzip the data set. Okay, and process the text data. So execute this code, please. Okay. In this practical session, we will learn how to implement transformer. So we will learn how to implement the attention is all you need with my Vaswani, and this is full architecture of transformer, and we will start from very basic building blocks. So for this session, in this session, we will implement scaled up product attention and multi-head attention. So first, your first job is reshape function, which is input is the tensor in the shape of batch size by sequence length by embedding dimension, and your output must be batch size by number of attention head by sequence length by head dimension. So this function is essential function to do the multi-head attention mechanism. So we will start implement this transfer for score function. So I will give you 3 minutes to implement this function. After 3 minutes, let's check how to implement this function together. I will give you 3 minutes. Okay, let's do it together. So first, get to part of shape of tensor like this. And add self the number of head and add size of head dimension. So and reshape the input with the view function like this. So receiving the value of new x shape and return the x dot permute for matching the shape like this. So, okay, everyone follow the code. So this is the code for transpose for scores. And next, we have to write scale dot product. I will prepare the image of scale dot product. Your job is implement this multiplication function and scaling function like this. So the input is curry key value and tension mask like this, and your return output is attention output and attention weights. I will give you 3 minutes to implement this function. You should aware this is not multi-head attention version, so you do not have to consider multi-head attention. So, okay, I will give you 3 minutes to do it. Okay, let's do it together. First we have to do the torch the memo here. So the code would be mentioned. Wait.
Hmm?
We have to transpose like this because we have to last dimension of key transpose last dimension of key because we have to import the key and query, and then we divided the entire matrix by square roots of your embedding dimension, and then I will write the optional code um like this. Mm. This is the optional code because um this is implementation of tension mask, which is mask out padding or mask out the casual mask, which is masking feature token. And then we calculate the softmax with attention score. So attention weights would be like the softmax and softmax attention weight, but then -1. And then we will going to apply dropout. I think this is not written in the paper. Attention is all you need, but if you see the code in the attention all you need paper, they did the dropout, so we will do like dropout like this. Attention weight and the equals so. And then the output must be like this, matmul. Okay. So this is a code for scaled up product function. So, and let's implement multi-headed version of scaled up product. You also take Hajar masking into account, and the input is query, key, and attention mask. The query's shape is batched by number of tension head and sequence length and head dimension. And the key shape is batched by number of attention head and sequence length by head dimension. Okay. Ah, okay, I will. Yeah, okay, good. And the input value shape is like this. And the output would be attention output and attention weight. The attention weight is value of each attention, and attention output is attended output, the result of attention mechanism. So I will give you 5 minutes to implement this code. After 5 minutes, let's check together. Ah, this is the reshape function. this work for reshape. Okay, let's do it together. First, this is the similar with scaled up products. First, memo, but we have to divide into head dim, not embedding dim. Head dim like this, and I'll add attention masking mechanism. If this self dot attention mask is turned on, so it's not on. If causal mask, the size of causal mask gonna be sequence length by sequence length. So the attention weights gonna be like okay. So I will explain this. In this case, on squeeze for the first dimension and the second dimension of attention mask. The first is the batch size, and the second is the number of head. And then fill the attention weight with negative infinite with the position of the attention mask like this. But if it's not causal mask, the size of mask would be batch size.
Tao sáng ra đan kem rồi.
Attention. Thank you. Attention mask here. We have to increase the first batch size and number of head. If not the cutter mask, the size would be batch size by sequence. And so attention weights would be like this. Attention mask. In this case, we have to unsqueeze one and with the negative infinite. So, and rest of part is really similar to the scaled up product. So next and attention. For softmax with the last dimension. And then we will drop out, but as I said before, the dropout is not the necessary. Okay. It's optional thing. And no, thank you. Okay. So concat okay. Oh, so we can memo the attention probability and the value of matrix. And we have to transpose the second and the third dimension like this. And we have to contiguous the tensor in the GPU like this function. And we concat the shape as you see this equation. So so this is so similar code with here. I will show you this. So concatenate the equation like this and project the weight. And the final output would be the attention output and the attention weight. So, okay. And then project the query and key value with this linear project matrix and self-attention and transpose key query value and do the scale the product and get the result here. Okay, let's move on to the position-wise fit-for network. In this section, we will implement position-wise fit-for network, this one. And I think it's pretty the simple code because it is same as this equation. And I give you simple code block here. So your job is to implement position-wise fit-for network here. The input is x. Input to a layer shape is like this. So I will give you just 1 minute to implement this position-wise fit-for network, and let's check together. Okay. Okay. We don't have much time, so let's do together. So first you can residual like this, and first we have to activate the value, pass the value activation like this. So activate function with self dot w1 x like this, and let's drop out like this. Okay. And then we will do linear once again. And then drop out again. And then the return would be the residual connection, X plus residual, because residual connection for preventing the gradient vanishing problems. So this is implement the position Y-fit for network, and let's implement sinusoidal position encoding too. This is what you do is implement sinusoidal position encoding here. So you just implement this equation. So it's very simple, and you can just use or NumPy or torch tensor to implement this equation. So I think it's simple. So I will give you 1 minute, and after 1 minute, let's check together how to implement this sinusoidal position encoding. Okay, because we don't have much time, so let's do together. Let's do together. So the PE, sorry, was and I what we talk about copy. I will use NumPy to implement this. So MP dot sign and then we can do like I plus 1 and data copy, and we do cosine like this, and and this one will be I plus 1 and divided into embedding dimension. So it's very easy, and we have to detach because for not training, we are going to not training this one, so we have to detach it. Okay, I think everyone followed this code, so it's easy. So now we have all basic building blocks, which is essential to build transformer. Let's implement transformer by step. First, we will implement encoder layer. This single layer of transformer encoder, this gray part. So first, I will give you 3 minutes to implement transformer encoder layer. After the input gonna be X and encoder padding mask. So X is the input of the layer of the shape, batched by sequence length by embedding dimension, and the encoder padding mask is binary bird tensor of the of shape. And then the output would be the encoded output of shape and the self-attention weight. This is a self-attention score. So after 3 minutes, let's check together. Okay, let's implement together. First, as we do the position-wise fit for network, we do residual like this, and the X and the tension weight pass the input to the, we have to pass the input to the self-attention layer. So free equal X and key equal X, and attention mask is encoder padding mask. And then we will apply the dropout on the attended output. So X dropout is X. Training equals delta training, like okay, and then add the residual plus X like this. And we apply layer normalization to the X to get this yellow block. For this yellow block, we will do like this, and then we will do the position wise feed forward like this. In this time we do not do the residual because as we made the residual in here, so in this time we do not the residual here. And then we will apply the layer norm on the top of the layer. So after do like this. And then we will get a return like this, but we can do like just this code, but in other many transformer package, they do like this code. So if you want to know more about this clamp value, you can see the other document, but we can do only until just here, but like other many transformer package code, I will add this code too. So I think this is 12 o'clock, but I will proceed the practical session. But if you have uh, uh any plan to go or something, you can go out. I will upload the full practical video on the classrooms. So okay, I will proceed the code. So this is the implement of transformer encoder layer. And then let's build the full transformer encoder together. The full transformer encoder is just to implement this picture. So we have to implement the input embedding and the positional encoding like this. So the input will be the input IDS and the tension mask. And the output is encoded the auto shape and the list of self-attention score of each layer. So I will give you 3 minutes to do this, to implement this code, and after 3 minutes, let's check together. So yeah, let's implement together. Okay. First, input dimension, input. So we first pass the input IDS to the token embedding, as you see here. And then we have to end positional embedding here, right? So okay. And then we have to add this, right? So Then we will gonna drop out. And then after with the practical session code, we have to visualize the positional embedding and the attention weights like this. So we have to make for store the attention score. We have to make the list for this, and we have to pass info picture sequentially. And so I do like this 4 iteration as this iteration do, and we have to repeat the end time of this gray block here. Okay. And so passing input feature end times like this. And then the self-attention score is appended like this, but we will detach it for not training. Okay, this is the encoder, transformer encoder. Okay, everyone do well, I think. So let's move on the decoder. This is the decoder layer of transformer. In this section, we will implement single layer of transformer decoder like this one, the gray one. And so first, you have to implement transformer decoder layer. The input would be X and encoder hidden state, the output from the encoder, and encoder attention mask and causal mask. This is for mask future tokens in decoder because decoder use causal mask. And the return is X and self-attention weights and cross-attention weights. So this is encoder decoder attention score. So I will give you 4 minutes to implement this decoder layer code. After 4 minutes, let's check together. Okay. Let's check together. Okay, let's. First residual connection here, like this, and we will do the self-attention. So So we add keys to the layer states, and we will having this kind of attention quasar mask. Okay, and then we will gonna be to drop out the X. We will apply the drop out. And then we will do the residual like this for vanishing the gradient vanishing problem. And then we will apply the layer, self-layer, attention layer norm. So cool. Okay. And then we will implement the cross attention block, like residual equal X, and we will do the cross attention weight like this. Let's self that. We will set in curry as X, and key is the output of the encoder. So key is space, and we just applied encoder padding mask to here. Like here. So, and then we will do the same as upper, like do like same as upper like this. And then as we do the encoder part, we will do the position wise feed forward. After position wise feed forward, and we will do the fire layer norm here, normalization to the X. And then the return would be dot X and self-attention weights and the cross attention weight. The cross attention weight is like this one. So this is the code for the decoder layer. And then let's move on to implement the whole full transformer decoder as you see in this picture. So your job is to implement the transformer decoder here. So input is input IDs and encoder hidden states and attention mask and quasar mask here, and the return is X and the cross attention scores. So okay, I will give you 4 minutes to implement this, and after 4 minutes, let's check together. Okay, let's check together. So let's implement together. This is same as the embedding process. So positions would be the self dot embed position, and like this. So first, the X would be embed tokens with and we will add X with the positions. So and we will drop out, apply the dropout. We do so much to implement this course, so I think you guys will be familiar after this practical session. And then for decoder layer, we also do like this attention score here. So we keep the output scores as visualization step. And as the same, as to do just same as encoder step, we have to do the end time of this block. So we do the isolate the decoder layer. So um, this one would be oh, oh sorry. Like this. So in the decoder layer, we will put X and encoder hidden states and encoder mask and the casual mask for the decoder. And then we will calculate the cross attention score for the visualize the attention score. So we will append like this and we will detach it. So this is the code for the decoder layer. And then let's combine encoder and decoder in one place. So in this transformer code, you have to implement generate mask for encoder and decoder attention. So the input is the long tensor of SRC and TRG. This is the input to the transformer shape and the decoding target of the transformer shape. And the return is encoder attention mask is the padding mask for encoder, and then the casual mask for decoder is decoder attention mask. This is the output of this function. So I will give you 3 minutes to implement, and after 3 minutes, let's check together. Okay, I will go back to decoder code. This is the decoder code, and this is the same as embedding the process, the same as encoder for 2. Here is this one. Okay. This is the decoder layer code. Okay, let's implement generate math code together. So, this line generate a mask for encoder's attention mechanism. It compares its tokens in the SRC to the index of the pad token in the source vocabulary. If token matches the pad index, the corresponding entry in the mask is true, and this is then transferred into the specific computing device like CPU or GPU with the two device. And the encoder ignores this position during the tension calculation, and TMP is so TMP of the size equal to the length of the target sequence. And this matrix is filled with the true values and is a type of torch bowl. Then we do the math like torch dot arrange TMP dot size -1 and device equal device. And to create one dimension tensor mask that contains sequence of integer from 1 to TRG does 1 to size 1 minus 1. And then we will have to so to generate the causal mask for the decoder attention mechanism, and it uses mask tensor to fill the lower triangular part of the TMP matrix with the false. So after this code, we will generate the mask, and the output will be the encoder attention mask and the decoder attention mask. Okay, so this is the transformer code, and then we will evaluate and train and evaluate the code. But this is very similar with code with the Wing 9, so I will do not explain the code. So this is just the hyperparameter, so you can change whatever you want. And so you can change the approach or learning rate or whatever you want. And you can update the pad index to use new vocabulary index like this, or so this is just a design for the code. And after assign any config like this hyperparameters, and you can train and evaluate the codes. So for the time issue, I will move on. I will skip the training and eval the code. After in your home, you can do just yourself or study this transformer code on your own. And you can see the drop of the validation loss, like here. And I will just show the visualization results just in here. So when we do the positional embedding metrics like this, we can see we can visualize the positional embedding like this with this code. So this is the output of positional embedding metrics. And then we can also visualize the attention. So if it's a layer 1, each word is attention like this. So you can do this code in your home and see how the attention going with different layer and the cross attention and self attention. Okay, you can check yourself at home. So okay, this is the end of the all practical session. So if you have any question, feel free to ask on Classroom or my email, and you can go out. 실습은 여기서 끝내겠고요. 혹시 질문 있으시면 클래스룸 같은데 올려주시면 답을 달아놓겠습니다. 수고하셨습니다.